sir?
Yes, yes. Yeah.
Good morning. VIT Bhopal University is celebrating National Science Week during 25th February to 3rd March 2022. This event is catalyzed and supported by National Council of Science and Technology Communications, NCSTC, New Delhi, and Madhya Pradesh Council of Science and Technology, Bhopal. On behalf of VIT Bhopal University, I welcome you all to the second lecture of the planned lecture series, which is to be delivered by Dr. Vilas Shelke. He is CEO of Recharge Energy Private Limited, and he will be speaking on E is equal to MS square, energy for mobility and stationary storage. Myself, Dr. Sharat Tripathi, and I have Dr. Pradeep Kumar Keshav with me. We are your hosts for today's interaction with our esteemed guest. Dr. Shelke has joined us. We are quite privileged and delighted to host you, sir, on this platform of VIT Bhopal University.
My pleasure. Thank
you.
So
we'll have the lecture first, and then we'll open the session for Q&A. You can post your questions in the chat box, and we'll summarize those questions, and then we'll one by one we'll ask to our esteemed guests. So now, at this moment, I request my fellow colleague, Dr. Pradeep Kumar Kashyap, to introduce our today's speaker to the audience.
Thank you, sir. Dr. Shelke is an academic researcher turned entrepreneur in his 22 years of research career. He worked at Bhopal, India, Paris, France, Tuscaloosa, and Western USA in various capacities. The primary focus of his research endeavor has been multifunctional oxide material in bulk, nano, and thin film form. He did establish an expertise with several highly cited publications, patents, and recognition by International Center for Diffraction Data. He has been recipient of Indo-US Science and Technology Forum Fellowship, French Embassy Fellowship, and DST Young Scientist Award. Recently, he launched a deep tech startup, Recharge Energy Private Limited, as Indo-UK joint venture. It is committed to cater India's renewable energy need within domestic ecosystem. The company is developing fully indigenous, import-free, much safer and cheaper rechargeable batteries based on sodium-ion chemistry. We welcome you again, Dr. Vikas Shelke. It's over to you, sir.
Thank you so much. Thank you, Pradeep, and thank you, Sharad. It is a pleasure for me, and good afternoon, all the participants. Just allow me to share my screen in a moment, and then, yeah, we'll go through it. Is the screen visible?
Yes, sir.
Okay, so you all know this fellow on your screen. It is a source of a tremendous amount of energy. It is omnipresent. It is present everywhere. It is there in your food. It is there in your breath. It is in corona vaccine. It is in coronavirus as well. It is in flower, and it is in fire also. So it gives us energy. The nucleus contains infinite amount of nuclear energy. The electrons, when they move from one place to the other place, they give us electrical energy. And when they revolve around their mean position, we get magnetic energy. And when they interact with each other, we get chemical energy. And energy is what we need. Today, I will be talking about energy for mobility and stationary storage. Don't worry about this equation. I'm not going to solve or derive Einstein's equation. This is just synonym to express the energy for mobility and stationary storage. So mainly I will be talking about the electronics, mechanics, and economical part of rechargeable batteries. So just relax. It is a Sunday afternoon and nice weather outside. So feel free to ask your questions and any doubts if you have. We all know that we get energy from thermal or nuclear or hydrothermal power plants. And the energy is transmitted through miles of transmission line and tons of transformer, and it comes to your home for your utility purpose. We all know that this kind of energy supply is non-renewable. There are limited sources of fossil fuels. It creates a pollution. There is huge infrastructure is required in the form of transmission lines and transformers. There is a maintenance and there are 30% losses during transmission itself. So there is an alternative way of renewable energy through solar energy, which is available abundantly. It is a green source of energy because there is no pollution. It can be localized. You don't need all the transmission line. It can be generated where you want it. It can be stored in a battery. It is mostly maintenance free and there are only 3% of losses. And the interesting part is solar energy is DC electricity, and battery also stores in it in a DC form. And nowadays, most of the applications like your light, LED lights, LED TV or home appliances, or most of the gadgets also, they work on DC electricity. So we really don't need a 50 hertz 220 volt AC supply. And slowly the world is changing from AC to DC. How you can see it, there is a huge deployment of batteries in all the sectors. For rural electrification, you can use solar panels supported by battery. You can use batteries for clean water supply in remote or rural areas. For telecom towers, you can use batteries, again for replacement of diesel generators. Of course, all your appliances or gadgets, they use rechargeable batteries. And in the mobility sector, now you have two-wheeler, four-wheeler, even there are trains and aeroplanes operated by batteries. And just to mention, these are not toys, these are real aeroplanes and real trains running on the battery. And of course, there are mega projects like Google data center in Nevada with 50 megawatt hours of electricity. It is fully renewable and fully stored in a battery. There is no transmission line supplying electricity to Google data center. And the famous Elon Musk project in Australia with 194 megawatt hours of battery deployment. And there are many such mega projects across the world where the batteries are used for energy storage. Today, primarily, we will focus on the electric mobility part. We will try to understand the deployment of battery for electric mobility. Suppose you have this beautiful car, and if you see under the seat of this car inside the chassis, there lies heart of the car or the lifeline of the car, which is a battery. It includes different number of modules and more than 8,000 cells inside it. The cells can be of various size and various shapes. The standard one is 18 mm diameter and 65 mm length cylindrical cell. Prismatic cell is a hard case celling. Some of the applications prismatic cells are used. Pouch cell is the most flexible one. It can be of any size, any shape, or any capacity. And the standard coin cell, which we use for many electronic toys or your car keys or remotes. Now, whatever type of cell is there, the basic mechanism for these batteries is same for right from the Baghdad battery or Voltage battery. Every battery essentially has a cathode. There is an anode. In between these cathodes and anodes, there is an electrolyte and a separator. So when the battery is fully charged, the ions, particularly in this case, lithium ions, they are accommodated on the rocking chair format of an anode. There is enough space inside the anode material so that the ions can comfortably sit there. And when you use this battery, it gets discharged. So the ions move from anode to cathode. And when all the ions move from anode to cathode, the battery is discharged. Again, when you charge the battery, the ions transfer from cathode to anode and the battery gets fully charged. Now, how many number of ions are accommodated per unit volume or per gram inside this anode material or cathode material? That defines the energy density of the battery. And how many times these ions can shuttle between anode and cathode? That defines the cycle life. That it means the charging and discharging cycles of the battery. So for general purpose, we desire the energy density should be higher than maybe 100 watt hour per kilogram. And the cycle life is expected for commercial battery. It is above 3,000 cycles. So a battery can last for 7-8 years comfortably. And then after that, these ions get trapped on either side on anode or cathode, and the battery functioning or battery capacity minimizes. So then you have to replace the battery. Now, if you see the process for a battery pack fabrication inside a e-mobility manufacturing unit, then the battery pack it's of a tray and casing. Inside this tray and casing, there are battery modules, and the modules, each module have a different number of battery cells. These battery cells consist of electrodes, anode and cathode mainly, and these anodes and cathodes are made from a material powder. Now, for this entire part, from the battery pack and battery cells manufacturing or electrode manufacturing, there is no as such rocket science. It is a same thing for all kinds of battery. But the innovation mainly occurs on this powder, the material which is used for fabrication of electrode. That is the part where most of the parameters or most of the properties of a battery are governed or defined. So the most common choice for commercial battery anode is a graphite material. You know that graphite has a layered structure, so there is a space between these different layers, and the lithium ions, being a small ion, can comfortably sit in between these different graphite layers. So large number of lithium ions can be accommodated inside the graphite layers, and that is how the graphite has a very high energy density or energy capacity, because there is enough room for more number of lithium ions. For cathode material, the original choice was lithium manganese or lithium cobalt oxide, for which the Nobel Prize was awarded to J.P. Godinap and Whittingham. So then to increase the capacity of this cathode material, another version or another variation with lithium, nickel, manganese, cobalt oxide was invented. It is popularly known as NMC battery, and the lithium manganese oxide is LMO battery. And a more cheaper version of this battery is a lithium iron phosphate battery, which contains iron and phosphate. So, so far so good, no issue with battery. But if we see the economics of a battery, then this LMO battery has 6% of lithium and 94% of manganese. NMC battery, which has a higher energy density, it has 11% of lithium, 29% of manganese, 30% of nickel, and 30% of cobalt. The another variant of NMC battery with 11% lithium, 8% of manganese, 72% of nickel, and 9% of cobalt. So these variations are basically made to increase the energy density, cycle life, and as well as to control the cost of a battery. And in the last year itself, there has been 496% increase in the cost of lithium. That is mainly because of there is a boom in electric vehicle or e-mobility. The cost of magnesium increased by more than 200%. Cobalt, which is already very costly, it has registered the increase of more than 100%. And this is the situation in 2021 when the battery deployment is around 200 gigawatt hour worldwide. And by the end of this year, the battery deployment is going to increase up to 2000, means 10 times increase will be there in a battery deployment. There will be slight increase in a consumer electronics market, a significant increase in a stationary storage market, but there is a colossal increase in e-mobility or electric vehicle battery deployment. So you can imagine the situation when there is a 2000 gigawatt hours of battery deployment, then what will be the cost of material? So the battery demand is increasing exponentially, but the supply may go down. So there is a critical problem. A more critical problem is with the resources. These are unevenly scattered across the world. Lithium, which is a new petrol, it is available only in few selected countries like Chile, Argentina, and Australia. We don't have lithium resources. Similarly, cobalt, the another important element, it is available mostly in a Republic of Congo. And nickel is available with again with few countries. So these three vital elements, lithium, cobalt, nickel, we don't have resources for them. China has certain kind of resources, but most of these mines across Argentina, Chile, Congo, and South Africa have already been acquired by China. So China has a strong control over the rechargeable battery manufacturing. About 80% of global battery manufacturing is done in China itself. United States has only 8% share in the global capacity, and that also because of that Tesla Panasonic plants in Nevada. India don't have end-to-end manufacturing of rechargeable batteries. So our self-reliance in energy sector is vitally endangered. If China desires, our electric mobility will turn into no mobility. So what is the solution then? So we need an alternate technology. The commercial lithium-ion battery uses graphite as a anode material. A new technology based on sodium ion has been pioneered by Faradian company based in UK. And it started with the invention of porous carbon as an anode material, because graphite is not suitable for sodium ion. Sodium is a bigger ion than lithium ion. So the spacing between these graphite layers is enough to accommodate lithium, but it is not enough to accommodate sodium ion. So when this porous carbon was discovered as an alternative anode material for sodium ion battery, then only this battery could operate at a sufficient energy density. For cathode, sodium transition metal oxide or phosphate is used as a cathode material for sodium ion battery. And you know that sodium is abundantly available across the world. Sodium salt is everywhere in the world, particularly in India. It is abundantly available. We will not need lithium, cobalt, nickel, or manganese for sodium battery. The electrolyte is NaPF6, just similar to LiPF6. Current collector for lithium-ion battery is essentially copper and aluminum, but for sodium-ion battery, it can be aluminum at both the ends. And the common choice for sodium-ion battery is in the form of coin cell or pouch cell. And the most importantly, the raw materials required for lithium-ion batteries are mined outside India. For sodium-ion battery, it can be all domestic. Porous carbon is abundantly available with the bio waste or agro waste. You can derive the porous carbon from any kind of agro waste. And sodium, of course, is abundantly available in India. And again, safety is a major concern with lithium-ion battery. When it comes to safety, lithium-ion battery is not a flower, it is a fire. I mean, it catches fire. So comparatively, sodium-ion battery is much safer than lithium-ion battery. Now, this sodium-ion battery technology is being talked so much. Is it really a viable technology, or is it a commercially successful technology? So any battery technology, the longevity or the viability of the technology is defined by its ECG. It means energy density, cycle life, and greenness or safety of the battery. So if we see the development of rechargeable batteries, for example, for lithium-ion battery, it started booming around 2000 when the energy density was around 150 watt-hour per kg. So Sony and Panasonic, they developed these NMC batteries with energy density as high as 240 watt-hour per kg. Still, these batteries have very high energy density. The low-cost version is being manufactured in large quantity by Seattle, China-based company, and these are LFP battery. And then in 2015, Faradian started this innovation with sodium-ion batteries, and they have already achieved energy density higher than the LFP battery, and we are trying to catch up with them. There are many important parameters for battery commercial batteries. One is the energy density. So you can see that already sodium-ion batteries perform better than the at least LFP battery. The power density for sodium-ion battery is better than LFP battery. The cycle life is more than 3000 cycles for all these batteries, NMC, LFP, or sodium-ion battery. So comfortably, sodium-ion battery can be used for 7-8 years. In fact, the cycle life for sodium-ion battery can be increased up to 5000 cycles as well. So the battery will have a longer life than lithium-ion battery. And of course, safety is better for sodium-ion battery. And cost is an important driving factor for the economy. So the cost of the battery means in how much watt hour you get in $1. So again, sodium ion battery is much cheaper than LFP or NMC battery because the cost of raw material. Sodium ion batteries, the raw materials required are all low cost materials. Unlike lithium ion battery where lithium is costly, nickel is costly, manganese is costly, copper is even costly. So of course, this sodium ion batteries will be low cost, faster charging, and better safety. And at Recharge, we are trying to develop a proprietary material for cathode and anode. So as you know, the main innovation is done on the material side, mostly on cathode side and on anode side. So for cathode material, there are three families of materials which are commonly used for these sodium ion batteries. One is a layer oxide sodium metal oxides. So don't be worried about these structures. As a physicist, we have habit to explain these any phenomena on the basis of these ball and rod structures. So simply, it just simply signifies that how the ions are accommodated or where the ions are located inside a crystal structure. So one choice is where you have a sodium composition with transition metal and oxygen. And there are different variations of these structures, like with orthorhombic structure or prismatic structures. Second is family is polyanionic fluorophosphate material. Again, there are sodium ions and then fluorophosphates are used to stabilize the structure. And third family is Prussian blue analogs, where again there are different variation. So all these three families, there are variety of compositions with different values of specific capacity and different values of working potential. So here you can see a large number of compositions. You don't need to understand what these compositions are, but this is just to show that by varying the composition of material, you can achieve different specific capacities, or you can achieve different working potentials. Now, while using these various compositions, the important parameters or important aspects are, one is a phase purity. Any family or any composition you use, you cannot afford to have impurity phases, because if there is impurity, the physical properties like electronic conductivity, ionic conductivity, and many important parameters will be affected by the presence of impurity. So you essentially need your cathode material to be phase pure. Second important thing is a structural stability, because when you make these materials, the structure should remain stable, particularly when the sodium ion is intercalated or released from the structure. For many applications, the structure is stable because you don't remove any ion or any atom from the structure. But in this case, essentially the sodium ion has to go from cathode to anode or anode to cathode. So during this transport of sodium from one end to other end, the structure should always remain stable. It can tilt a little bit, but nevertheless, along with its tilting, it should keep its stability for the sodium ion accommodation and sodium ion release as well. The ionic and electronic conductivity of a material plays important part, because the number of ions transporting from one end to the other end is defined by the ionic conductivity of material. And at the same time, electronic conductivity is important, because electronically, if material is insulated, the electron transport happening in the outside circuit will not take place. So both ionic and electronic conductivity plays important role for this material. Specific capacity, because the entire energy density of the battery depends on the specific capacity of anode material and the cathode material. So the material, when we invent or when we try to synthesize cathode material, you have to always test the specific capacity of cathode material, anode material, and then collectively for a full cell combination, you have to measure the energy density of the cell. And cyclability also is important, because how many times these ions can shuttle between cathode and anode. So how many cycles this battery can be charged or discharged, that entirely depend on the material used for cathode fabrication or material used for anode fabrication. Then from commercial point of view, the abundance of raw material and cost of raw material is very important. If you are dependent on import of raw materials, like in case of lithium-ion battery, then the battery will not be cheaper. There will be lots of logistic involved and expenses involved with the import of raw material and cost of raw material. Even if it is available within the country, it should not be very costly. Like copper is available in India, but copper is much costlier than aluminum. So aluminum is better choice to reduce the cost of battery. And similarly, sodium and all these material used in the fabrication of cathode, like there you can see the compositional variation. There is manganese, cobalt, nickel as well. They may give you a better performance, but for commercial purpose, you should know how to exclude these materials which are not domestically available or which are costly material. Again, there are some elements like say vanadium or chromium, they can give you better performance, but there are issues with toxicity and safety of these elements. So again, you have to think that you have to make a compromise sometimes on the specific capacity or cyclability to avoid toxic or unsafe elements inside your battery. Similarly, for anode material, for anode, you don't have much choice. Either you can use a graphite or porous carbon or hard carbon, it is called. There are materials which are being tested for, but the most successful or commercially viable material is a hard carbon or porous carbon for sodium-ion battery. It is called hard carbon because it is harder than graphite. You know, graphite is a very soft material. So the other form of carbon is a diamond. Diamond has a sp3, sp2 hybridization, but this hard carbon is a mix of sp2 and sp3 hybridization. So it is harder than graphite. So it is called hard carbon. It is also called porous carbon because there is a porosity, there is a space between these carbon layers, random space is there where this sodium ion can be accommodated. So the porosity of this anode material is the very important parameter for anode material. This anode material can be derived from various sources. In fact, carbon is an integral part of many biomaterials or agromaterials. So this carbon can be derived from charcoal, biochar, potato starch, rice, olive, walnut shell, sugar cane, and even coconut shell or coconut shell charcoal. So anything you can think of. In fact, in China, they are deriving carbon from chicken waste, fish waste, or pig bones. So anything, but of course, while deriving this carbon from these kind of natural resources, you have to consider the factor that the carbon should have sufficient porosity, it should have purity, and there may be certain kind of functional group attached with it so that it has a good conductivity. So on the basis of these parameters, then you have to define that from which source you are deriving your carbon. So now you have a anode material, already you have selected your cathode material. So then it is a time to combine these anode and cathode materials to make a battery. So the process of making a rechargeable battery is quite simple. It is being used for all the types of battery. Even it is same for lithium-ion battery or sodium-ion battery. So you essentially need a powder of carbon, powder of cathode material, and powder of anode material. Then by using a binder, you make a slurry of this powder separately, and then you make a layer on the certain kind of electrode or current collector. You can use copper or you can use aluminum. Aluminum, as I said, is a preferred choice for sodium-ion batteries. So after depositing these layers of cathode and anode material, then you have to dry it or allow to settle the layer, and then you can cut it in the form of electrode. So for coin cell, if you are going to make a coin cell, then you cut it in the particular size of the coin cell case, and then you cramp it in the form of coin cell. So there you cramp the layer of cathode and anode, and in between you have to put the separator and the electrolyte. Similarly, to make a pouch cell, you have to get the pouch case, and inside the case again you put single or multiple layers of cathode material, anode material, in between separator. Then you put the electrolyte. But of course, these processes are done in a vacuum or inside a glow box, because the material which you use as the electrolyte cannot be exposed to the environmental condition. So this has to be done particularly when you put the electrolyte inside and seal the pouch cell. So that process has to be done under vacuum condition or inert atmosphere condition. And then you connect the taps to connectors for the electric supply, and then your battery is ready. So in this entire process, that main focus is on development of materials on cathode side and anode side. So to allow you sufficient time for your questions and answer, just I will conclude the session. So you have an electric mobility vehicle. Inside the electric vehicle lies the heart of the mobility, that is battery. For a healthy heart, you need to have a good ECG. It means it should have good energy density, good cycle life, and the greenness or safety parameter. And for good ECG, you need to have a homemade, healthy, and affordable food. So thank you so much for your attention. At Rechargeable, we are trying to resolve or solve this equation, energy for mobility and stationary storage, with the entire focus on make in India, develop in India, and startup in India. And the plan is to supply batteries to the world. And taking a clue from Edison's sentence, once famously Edison has said such a thing, that we will make a battery so cheap that only the rich will use petrol. So that's the ultimate goal. Thank you so much.
Thank you, sir, for such a detailed discussion and your presentation on that basics of the batteries. So we have with us Dr. Avirup Das. He is my fellow colleague here at VIT Bhopal. He has posted some questions. So I'll request Dr. Avirup Das to unmute himself and please ask your questions yourself, sir. We'll have interaction.
Okay, good afternoon to all of you. So it was a great presentation by Dr. Shelke. And as Dr. Shelke has said that, yes, India is trying for the best to be self-sufficient in the rechargeable battery sector. So, sir, I have a query, like a rather query, not a question. It's my own curiosity, sir. In India, there are some people. A lot of research is going on for prismatic cell or coin cell or cylindrical cell manufacturing for the lithium-ion batteries.
Yeah.
Sir, when we have a proper sodium cells, cathode, anode, and electrolyte, which can be commercialized in a large scale, can this manufacturing unit will work for sodium-ion batteries?
Yeah, that's a very good point from a commercial point of view, because whenever a new technology is launched in the market, the important aspect is the infrastructure. Because now for electric mobility, when this two-wheeler and four-wheeler came in the market or started coming in the market, the infrastructure required for electric mobility vehicle is different from the infrastructure required for petrol or diesel vehicles. So the companies, they had to set up a different facilities for such a setup. But of course, for e-mobility, the cost involved is less than installing facility for petrol or diesel vehicle. Similarly, the important part is for battery. So because in India, mostly there are a battery manufacturer, but one thing is there that in India, nobody is manufacturing battery cells. They are just assembling the battery packs and the battery management system, which is required to charge or control the charge-discharge cycle of the battery. So in India, still, there is no company which is manufacturing entire, even lithium-ion battery, end-to-end manufacturing. I mean, most of the companies in India, like Exide and Tata and other, Amara Raja, they have collaborated with the Chinese company. Chinese company supplies bulk amount of these pouch cells or electrodes, and then the casing and the battery pack assembling is done in India. But now there are quite a few companies which are venturing in the manufacturing of lithium-ion battery to begin with. But the good thing is that the same assembly line which is used for lithium-ion battery manufacturing can, as it is without any change, can be used for sodium-ion battery manufacturing. Everything will remain same. There is no change in pouch cell fabrication. There is no change in electrode coating, or there is no change in sealing or anything. The entire assembly line, as it is starting from the 0.0 to the end deliverable, it will be the same for lithium-ion and sodium-ion battery. Only when you make the powder and when you make the slurry, so instead of lithium based material, you will use sodium based material. Otherwise, everything will remain the same.
Okay, yes, sir. Thank you, sir.
Out of curiosity, one of our students has asked, how can we generate electricity through a piezoelectric material and extract it?
Okay, yeah, so that is good curiosity, although different from the working of a battery. But when we want to generate because battery is a storage unit, it cannot generate electricity, it can just store the electricity. Now the question is from where the electricity will come for a battery unit. So one option I showed is a solar plant. From solar, you can get the electricity. Similarly, there are different types of mechanisms. So one is thermoelectric. So in case of thermoelectric, when you create a temperature difference between two ends of a material, then a potential difference is set there. So that gives you voltage. So again, research is going on in thermoelectric materials as well. Just like a solar panel, it converts the radiation into electrical energy. Similarly, thermoelectric material converts thermal energy into electric energy. But the problem with the thermoelectric material is that the conversion efficiency. Like at early stage, even solar materials also had this issue. But now these commercial solar material, they have this efficiency beyond 15%. But for best thermoelectric material in the world, even the conversion efficiency is less than 3%. So you have to generate the temperature gradient, heat difference, and then with that sufficient heat difference, you get an energy which is only 3% of the energy required for the creating a temperature gradient. So there is one application which is quite academically it is discussed that in a vehicle, petrol or diesel vehicle, the engine generates lots of heat, and that so can we use a thermoelectric material to convert that heat energy into electrical energy? So in principle, it is definitely possible to convert the thermal heat into electricity, but the conversion efficiency will be very small, and you will get very small amount of energy. But of course, since the heat is being wasted, so anyway it is a waste, you can always get at least small amount of energy through thermoelectric conversion.
Thank you, sir. There is one question. We have our student, what's her name? Akanksha Jha. And she is asking that, is there any way to tackle the problem of scarcity of lithium with the increase in its demand?
Okay, so there is only way that you need alternative for lithium. There is no other way because an alternative is sodium. But of course, the other way, if you want to think that how to deal with, so there is one more option, that is to recycle. So most of these battery materials like lithium, nickel, manganese, cobalt. So once there is a deployment of large amount of large batteries, then there is one option is being discussed or being tried by commercial entities, that can we reuse this lithium or cobalt nickel for the batteries, the way we recycle plastics. Can we recycle the batteries? So of course, it is possible to recycle the batteries, but the cost involved in the process of recycle, because lithium is very reactive material, cobalt, nickels are very reactive materials. So you can break the battery, take them out and separate them. But the cost involved in this recycling is again quite high. But yes, that option is there, that you can reuse the lithium to mitigate the problem of lithium scarcity. But of course, the more cheaper option is in terms of sodium-ion battery.
We have our one more fellow colleague, Dr. Ashok Baral. Ashok sir, you can unmute yourself and then you can ask your query. Ashok sir? Are you there?
Yeah. Good afternoon, sir. Sir, myself, Dr. Ashok Baral. I have been working for this garnet-based lithium-ion conductors in the University of Calgary, in the group of Thangadurai group. So I have some curiosity about the Na-Cathode use as electrolyte in sodium-ion battery. What is the chance for that? I know this is a very porous material, and also conductivity range should be order of -3 at room temperature, isn't it?
Yeah.
So, do you have any opinion about it?
Yes, because when these sodium-ion batteries were discovered, the first choice was this Na-Cathode material. Na-Cathode basically it is a sodium-ion ionic conductivity material. So the layered oxide which we are talking about, those are in the similar family. So originally these Na-Cathode materials were and now also these Na-Cathode materials are being used. But the only thing is that since the cycle life of this material is less and energy density is less, that is the reason these various compositions are tried, or different options are tried for that through a substitution. So when basically we do a substitution, that means we increase the structural stability. For example, when we substitute iron or manganese, then that improves the structural stability. Because the main working of battery depends on transport of sodium ions. But when we remove or intercalate sodium ion, then the structure stability or the accommodation of sodium ion plays important role. And for that, for improving those parameters, we use different kinds of composition or different kinds of substitution. So same thing happened with Na-Cathode material. So through different types of substitution, this energy density and cycle life of the material have been increased.
Okay, sir. So maybe I will interact with you later with a lot of things, because I work in fuel cell and batteries, so I will have a lot of interest in.
Yes, sure, definitely. You can get my contact from Sharad, or you can contact me on LinkedIn.
Thank you very much.
We'll keep in touch.
Yeah.
One of our students, Suresh Babu, he has asked, how about the zinc ion batteries in the future utilization in vehicles?
Okay, so zinc ion batteries, there are different varieties, because when we talk about batteries, basically there are two types of batteries: primary battery and secondary battery. Primary batteries are those batteries which cannot be recharged, and secondary batteries are those which we can recharge. So there are zinc air batteries. Those will be really very cheaper version, because there you have air itself as one electrode. But when you use like a zinc air battery, that is use and throw kind of batteries. Like for some application, for low power application or low energy application, zinc air batteries are quite suitable. Like for example, that ear machines, their zinc air batteries are quite popularly used, or some of the applications in sensors that zinc air batteries can be used. So not only zinc air, there are many other chemistries. There are at least 3 to 4 dozens of chemistries for batteries, and each has a different sector or different application. Some of them are rechargeable, some of them are not rechargeable. Some has a very low energy density, but a very low cost. So this way, there are many kinds of batteries. But for large energy storage, or like electric mobility, or for stationary storage application, currently the preferred choice is either lithium-ion battery or sodium-ion battery.
Purnaditya has asked what different types of green energies exist or can be created in a large scale that can be used in propulsion so that we will have less pollution.
Pardon? It is about clean energy. Can you repeat the question?
Sir, he has asked what different types of green energies exist or can be created in a large scale that can be used in propulsion so that we will have less pollution.
Okay. Yeah. So when it is the pollution issue is mainly related with when we use fossil fuels, like thermal power plant, we use coal. So there is of course thermal power plants generate use carbon dioxide, and also there is a wastage of heat. So global thermal power plants contribute to a large extent for global warming and for the carbon footprint or pollution. Similarly, we use fossil fuels in our our mobilities like petrol and diesels. So diesel vehicles produce again a large quantity of pollution. Petrol vehicles produce large quantity of pollution, and again there is a heating of an engine. So there is again it contributes global warming. So all these energy sources where we use fossil fuel, they are polluting and cause of global warming. So what are the alternatives? One is solar energy. Solar energy is abundantly available, but it is not all time available. We don't have solar for 24 hours. So when the energy is generated from solar panels, then it has to be stored essentially, and for that we need a battery. Second is a wind energy. You can use windmills. It is also a clean source of energy. We don't need any fossil fuel for wind energy. But again, wind energy is not all time available. So you have to store the wind energy in a battery. The same thing is done with the Google data center, because it is in Nevada region where they have cyclones and tornadoes as well. So there they are generating their electricity from solar panels and wind mills. So they have large number of windmills installed in near their data center. So both are the clean energy sources, but both need storage in the form of a battery. Tidal waves is also one option that you see in the sea there is during, for example, like during tsunami or during cyclones, the tidal waves, they also generate a huge amount of energy, and that can be converted into electrical energy. The same way, hydro energy is also a clean energy source, because for hydro power plant, you don't use any fossil fuel. But again, hydropower plant, it cannot be located everywhere. Wherever you have sufficient water supply and sufficient storage of water supply, plus the energy which can be released through these dams. So hydro is also clean energy supply. But again, for hydropower plants, there are environmental concerns, because to make a dam, you have to cut the forest, and it also creates a safety concern. So that because of those concerns, that hydro energy has not been that popular. So these are various options for clean energy. But for all these options, you essentially need storage of energy, and for those you have a choice in the form of batteries.
Thank you so much, sir. So on behalf of VIT Bhopal University, I'll again thank Dr. Vilas Shelke to spare some time from his busy schedule. And basically his talk was earlier planned by tomorrow, but due to some other engagements, we just preponed his talk today. And it was a very nice interaction with you, sir. We were quite privileged to have you on this platform of VIT Bhopal University. Thank you so much, sir.
Thank you so much. I really enjoyed the interaction. It is very good. All the best to all of you.
Thank you so much, sir. So for the participants, today we'll have another lecture by Mr. Dhananjay Rahul, and he will be speaking on science and technology in ancient Indian temples at 2:30. And by tomorrow, we will be having another lecture by Dr. Manjusha Shelke, and she is the principal scientist at National Chemical Laboratory, and she will be speaking on ultra capacitors, the high power flexible energy storage devices. So just stay tuned with us. VIT Bhopal has brought this program to you in association with MPCST and NCSTC. Thank you so much. Have a nice day, please.